So we are discussing the MMF distribution in space in the last class for DC machine, and we took a two-pole DC machine, I mean one north and one south pole. Am I audible?
Yes, sir, you are audible.
Yes, sir, audible, sir.
Okay. So we saw in the last class that how the MMF due to the pole and MMF due to the armature is distributed. Now, if we recap this discussion, then we should remember that the winding which we use for the pole, the field winding, is basically a concentric winding, just like a transformer, and therefore the distribution is a flat top. Okay, so the flux distribution is flat top, though the MMF distribution is rectangular. But in armature, we use distributed winding. So there are two distinct type of winding: concentric and distributed. For armature, we use generally the distributed winding. Okay, and as per the current direction, uh, and as per the given type of the direction of rotation and type of operation of machine, that means motor or generator. So we got a particular current direction, dot or cross, and accordingly we have this type of staircase distribution. And if the size of the stairs are very small, then we can approximate that staircase distribution to a triangular distribution. So that means the MMF due to the armature, we can think of a triangular distribution. So that's just we have shown here also relative to this main poles or field. So that also we have drawn, and accordingly the flux distribution we got similar, but in the interpolar region where you have the very high reluctance, there is a drop in the flux. So this we saw in the last class. So actually we drew two things: the
Sir,
distribution MMF.
yes, sir. Sir, just little bit, I want to ask about this MF distribution due to field coils. One thing I don't understand is that there are some reason in which MF would be constant due to field coils, but how can it and how and why why and how can it be zero in some reason? I mean, if you could just explain from some mathematics point of view, just I mean, if you see the
Which
formula
one?
MF equals to flux into reluctance,
Which one? MMF for?
sir, MF distribution due to field coils.
Okay. So MMF distribution
So my
due to the field coils is basically comes from the Ampere's orbital law. So wherever you have the coil, you will get the distribution. Okay, so your coil is up to this. If you see, okay, so if you see the poles, actually the coils are up to this. Okay, so this is the span of the coil, the concentric coil. That means this is the span, you can say. So up to this you have the coil. So therefore you have this type of distribution, rectangular distribution. Okay, and that you can get by this number of turns in the wheel binding that I already shown in the last class. So this is NF into IF. So that will be the height of this MMF. So this MMF height will be NFIF. Okay, and the opposite also you will get the same because there also you have the same current flowing and same number of turns. And so you will get the MMF only inside this. Suppose you have a coil like this. Okay, so you will get the MMF only inside this, not outside this. That we can say from this Ampere's orbital law. Okay. Anything more?
Yes, sir.
স্যার জিএনএ আর এমএনএটা একবার এক্সপ্লেন করবেন, মানে জিওমেট্রিক নিউট্রাল অ্যাক্সিস
that
আর
I will
magnetic?
explain today. That I will explain definitely today, because that I didn't discuss in the last class.
Okay.
So that definitely I will discuss. But once we have drawn the distribution, the MMR flux distribution, then only we can discuss. GNA anytime we can discuss, but the MNA, for MNA we should know the distribution. So his point is clear, why we are getting this rectangular distribution. Anybody wants to add any points here? Okay. Now the geometric neutral axis, or GNA, we get from this geometry. That means just inside this, between the two poles, geometrically at the center we get the GNA. Okay, so if we have the pole here and here, just at the middle we'll get the GNA. Okay, but the MNA, magnetic neutral axis, depends on where you will get, actually you will get the zero flux. The magnetic neutral axis depends on that. Now here, fortunately we have these two axes coincides. That means both the MNA and GNA, because you see here you have the GNA at the center, and MNA also. That means the zero crossing of the flux distribution also occurs there. So that means both the MNA and GNA we are getting at the same point. Is it clear? So magnetic neutral axis means where the flux crosses zero. So that gives me the magnetic neutral axis. And geometric neutral axis means just if we go for one pole to another pole, that means two consecutive poles from north to south, then exactly at the center we have the GNA, geometric neutral axis. That means that depends on the geometry only. Is this point clear? Can you tell me in the next curve what is the MNA? For this curve, what is the MNA?
যেটা বি
Sir,
বি এর
B
যেটা
B
মানে
pointer.
ফাই যেখানে 0.
Okay, so these are the points for armature curve. You get some MNA, isn't it? Magnetic neutral axis. But you see that there is a difference between this magnetic neutral axis of the poles or field winding and magnetic neutral axis of the armature. Can you tell me what is the exact difference? Let me ask somebody. Ananda Chakraborty.
Yes, sir.
Can you tell me
Sir, কিসের difference আরেকবার?
The MNA of the field winding,
Sir, কি?
field flux distribution, and MNA of the armature flux distribution. So that means this curve, and this red curve. So we have MNA over here and we have MNA over here in armature. So that means armature flux distribution and field flux distribution had MNAs in two different locations. What is the difference in angle? That I'm asking you. Is my point clear? I'm asking the
Sir, and yes, sir. Sir, here there are two different positions for MNA, whereas in the field coil there was only one position.
no field also always two
Because here the flux.
Okay, so here you see these two are the same point, na? This A is another MNA. So MNA always will be two. So that means
Yes, sir.
number of poles determines the number of MNA. So if there are 4 poles, then you will get 4 MNAs.
Yeah.
Isn't it? So here also we'll get 2 MNA and
yes, sir.
In field and as well as in armature. Now, can you tell me exactly the angle between?
Yes, sir.
Okay, so you.
Sir, I think it will be 90 degree.
Okay. It will be 90 degree. Okay. So anybody
so
else?
between B and C. Yes, sir.
Okay. So let me ask somebody else. Anubhav Rai.
Sir, একটা question.
Anubhav Rai.
Sir.
Yes, sir.
একটা question.
Yes, sir.
I'm coming back to you. So can you tell me what is the difference between these two MNAs?
So there are 90 degree electrical difference for the field flux. The MNAs are at B. No, the MNAs are at C. And for the armature flux, the MNAs are at B and D.
Correct. So that means this is 90 degree electrical. So you have to mention this point. So the angle difference between these two MNA is 90 degree electrical. Okay, so always it will be 90 degree electrical because as you are saying electrical angles, so that is irrespective of the number of poles. If there are number of poles are 4, then also you will get 90 degree electrical. And if there are number of 8 poles, then also you will get the 90 degree electrical. So somebody raised his hand, so let me go to him. So Nirmallo Nondi. Nirmallo Nondi, have you raised your hand?
Sir, geometrical axis, neutral axis আর ম্যাগনেটিক নিউট্রাল অ্যাক্সিস এই দুটো আমরা পজিশন দ্বারা ডিনোট করব নাকি একটা স্ট্রেট লাইন যেমন এসি স্ট্রেট লাইন আর বিডি স্ট্রেট লাইন দ্বারা ডিনোট করব?
That is the point or axis, whatever you can say. When you are going for
Sir,
this,
there is a
when you are going for this 1D, you can have a point. When you are going for 2D, then it's an axis. When we are going for 3D, then it's a plane. Are you getting?
Okay, sir.
So when you are moving in a circular path, then it's just a point, these 2 points. Okay, so when we are considering 2D things, then it's a line. Okay, now it is not a 2D thing. Machine is basically a 3D thing. So then it will be a plane. So geometric neutral plane, not axis. Is that clear? Anybody?
Sir, sir. স্যার স্যার ওই যেটা বললেন যে ওই 90 ডিগ্রি ইলেকট্রিক্যাল অ্যাঙ্গেলের ডিফারেন্সটা, হ্যাঁ ওটা তো স্যার ফিল্ড ওয়াইন্ডিং এর রেসপেক্টে তাহলে মানে?
হ্যাঁ, ফিল্ড ওয়াইন্ডিং এর রেসপেক্টে তো field winding, armature winding, whatever the number of poles you have in the field winding, you will get the same number of poles in the armature winding. The number of poles are same. So that is the thing. And this distribution will not change. Though the armature is rotating, so you should remember this. It's very important point. So here we have drawn two distributions. Listen very carefully. We have drawn two distributions, one for field winding, another for armature winding. Now you know that in a DC machine, field is fixed in space, but the armature is rotating. Though the armature is rotating, the distribution which I have drawn here will not change. This point you should understand and you should remember carefully, because you see, when this conductor will rotate and move to this conductor position, then it will change from cross to dot. That is the function of commutator. Commutation will take care of this. Commutation will take care of this job to maintain the flux distribution for armature fixed in space. Though the armature is rotating, but its flux distribution always be fixed in space. Is that clear?
Yes, sir.
Now, anything else? Somebody was asking something. কেউ কিছু জিজ্ঞেস করছিলে বলো? So this is very important point. Don't forget. হ্যাঁ বলো।
হ্যাঁ স্যার শুনতে পাচ্ছেন?
শুনতে পাচ্ছি।
হ্যাঁ স্যার বলছি আপনি জিএনএ টা কোথায় হবে বললেন? ওটা তো বি আর ডি পয়েন্ট হবে না?
কার জন্য?
জিএনএ মানে জিওমেট্রিক নিউট্রাল অ্যাক্সিস, ওটা তো স্যার মানে ওটা তো যেখানে আপনি সি তে রাখেন, ওটা বি আর ডি তে হবে তো?
কেন? Geometric neutral axis
ওটা তাহলে
A and C for this field, magnetic poles.
স্যার জিএনএ টা কোথায় হয় একবার বলবেন? ওটা
GNA টা হয় exactly at quadrature axis.
আচ্ছা আচ্ছা।
B and D is basically points on D axis, direct axis. GNA are placed in quadrature axis. So that means geometrically equal distance from two consecutive pole tips.
আচ্ছা, ওই সেন্সে হচ্ছে, ঠিক আছে।
Anything else? Okay. So now let me go for this resultant distribution. Now you have understood that these two distributions are fixed in space, though armature is rotating. Okay, and field is fixed. If the armature is fixed, field is rotating, then also you will get the same thing. Are you getting? Suppose in I have designed a different machine where my armature is fixed and field is rotating. Then also I will get the same thing. Both the MMF distribution will be fixed in space for this type of machine. Okay. Now, if this is the case, then there should not be two different distribution in this air gap. There should be only one distribution. That means these two flux will interact and there will be a resultant distribution in the air gap. So how to calculate this? To calculate this, we have to add these two curves. Okay, so this curve and this curve we have to add. Then we can get the resultant distribution. Okay. So the resultant distribution, if I draw in another curve, so how it will look like? If we add these two curves, the distribution for this field and distribution for this armature, so how it will look like? So let me shrink the screen. Okay. So what should be the distribution? Okay. Now here you see, here it gives 0 and here it gives this point. So that means this point if we add these two, I will get this value only, isn't it? So let me plot this value. So this is 1 point I am getting. Okay. Now here, what is the value we will get? Okay, so here it is, what is this distance in negative? So this much. And here you have very small positive. That means here you will get somewhere negative point. So that means in between the curve will intercept the 0. Okay. Now where it will reach the maximum? It will reach the maximum over here, because here it is very high flux value. Here also it is giving very high flux value. So here it will be like this, the maximum point. Okay. Now you just calculate these two value at magnetic geometric neutral. So this was the geometric neutral. Here you have the 0 flux contribution due to the field, but you have some sort of flux distribution due to the armature. That means you will get some positive value in the geometric neutral. So this is the geometric neutral axis, but here you will get some positive flux, because here you will get some flux contribution from the armature winding. Okay, so therefore uh, geometric neutral will not give a 0 flux or magnetic neutral. Okay, so the magnetic neutral will be shifted towards the right. Okay, so that means if we draw now this curve, so it will look like this. Okay, and it will be reversed in the other direction, so it will look like this. So this is the resultant distribution. So this is the resultant distribution of flux in the air gap. So have you understood this point? How we are getting this resultant distribution? Now sometimes what happens? So this value is very high, isn't it? So you see this value is very high. Sometimes your magnetic material doesn't support that very high flux density. So therefore, flux is clipped at that point. So due to saturation, this is called due to the saturation, flux is clipped at that point. So that is again a reduction in the flux curve. Okay, so that means you will not get that high flux value, but it will get a little less. Okay, so I am discussing this once more. Now, here you are adding these two flux, isn't it? Now, when you are adding, at some point you are getting very high flux, like this point. So this point you are getting very high flux. Now, whether you will get that flux or not, that depends on your magnetic material. Whether it will support, because magnetic material has its own beach curve nature. Okay, though you are adding, you are going linearly, but actually after this knee point, so this is the knee point of the VH curve. Okay, so after the knee point, there will be some saturation. This is called the saturation. So due to the saturation, there will be some reduction in the flux density or the flux value. Are you getting? বুঝতে পারছো এই জায়গাটা? Any doubt?
স্যার আরেকবার বলুন না ম্যাগনেটিক মানে স্যাচুরেশনের জায়গাটা ঠিক বুঝতে পারলাম।
Okay, so I am saying that here you have some distribution for the main field, and here you have some distribution of the for due to the armature conductor which are carrying current. So when we are adding these two value, we are getting a very high flux density or a high flux at this point. Okay, now actually when we'll measure, or if it is possible to measure the flux at every point in this air gap periphery, whether I will have this flux or not, the practice says that you will not get that high flux. Due to the saturation, you will get some less flux over there. Okay, so from your practice, we can say this, you will get some less flux value over there. Now, if we want to explain that actually, but analytically, when we are adding these two, or graphically, when we are adding these two, we are getting this orange point. But when practically we are measuring the flux value, we are not getting this orange point, we are getting this green point. Then why? Why we are getting this green point, not the orange point? Now the answer is this: you have a BH curve. So whatever the magnetic material you have used for this, maybe silicon steel or anything else, so that that magnetic material has its own BH curve or BH characteristics. Okay. Now, if this point, which we are marked by this orange, if that is beyond this knee point of the BH curve, okay, so due to this okay, so when we are actually adding, we are getting this point somewhere here, but we should go by this BH curve, so we should get the point over here. Are you getting? So we are thinking of this linear curve, but this is not a linear curve. So this you have to go by this saturation curve. Is this point clear?
Yes, sir. Now it is clear.
Okay, so you think then many points will be arised in your mind. So you ask me later. Okay, now so from this curve, if we want to make some observations, so what are the observation we'll get? We can note down. So let me write down all these points, the observations. So observations from the from the result flux distributions. Flux distribution. So before that, now let me clear some points and let me ask somebody. Bishal Bormon. Bishal Bormon.
Yes, sir.
Can you tell me that this new distribution of flux which we are getting as a third curve which I have drawn in this whiteboard, in which condition we are getting this? In no load condition or in a loaded condition of the armature?
In loaded conditions.
Okay, now you just tell me, in the no load condition, uh, what type of curve, flux distribution curve we should get?
No load condition.
In no load condition, what type of flux distribution in the air gap we should get? Hmm? Vishal.
Yes, sir.
Okay. Now I will ask somebody else. You just mute yourself. Ovidu Sarkar. Ovidu Sarkar. Ovidu Sarkar. When I'm calling you, if you don't respond, I will mark absent and I will put a marks 0 to this question. Now let me ask.
Sir, he has no mic. He's writing in the chat.
But mic is showing, na? Mic is muted, it is showing. Group lekha raha hai?
Yes, sir.
Can you answer this?
Hello. Sir, I think it will be the first among the three curves.
Correct. Mute yourself. Thank you. So yes, as he has pointed out correctly that if there is no armature current, so no question of armature flux distribution or MMF distribution, isn't it? If there is no armature current, no question of any armature MMF. And if there is no armature MMF, no question of armature flux distribution. If there is no armature flux distribution, it's no question of resultant curve. So you will get the same curve which we obtain for the field winding. So that means the first curve. Okay, so first curve is the MMF distribution at no load condition. So it's very easy question. You should answer this. Okay. Now let me note down the points. Okay, the first point is what about the resultant flux distribution? Okay, so is it similar to the actual field distribution, field winding flux distribution? No. Okay, now if we see the actual field winding flux distribution, it is very much symmetric in nature. Okay, so if we look back, this flux distribution which was there in no load condition, it was very much symmetric in nature, though it is not a sinusoidal, but it is symmetric with respect to the different axes and pole. So that means q axis, d axis, geometry neutral axis, whatever the axes are there, it is very much symmetric in nature. Now that symmetricity has lost when we have drawn this resultant flux distribution. So that we can write. So the resultant flux distribution is no longer symmetrical about the axis, pole axis. Okay, so that is the first observation. Have you understood this point? So you see here it is not at all symmetrically distributed. That is the first point. Now what is the second point? Second point, you see the flux, if we see the how that deformation occurs. Okay, now this was the original distribution of the field binding, but it is the distorted distribution. Now it has the flux value has increased at some point, and reduce at some point. If we think about this pole tips, so these are the two pole tips. So these are the two pole tips, isn't it? So these are the pole tips. Now, in which direction the motor is rotating? If I consider it's a motor, then which direction the armature is rotating? When we are drawing this distribution in linear, then in which direction the machine is rotating as a motor? Anybody?
Anti-clockwise.
Huh?
Anti-clockwise, sir.
No, that is
Anti-clockwise.
anti-clockwise is this. So that is already shown here. But I'm asking, when I'm drawing in a linear way, in which direction it is moving? In which direction it is rotating? Right to left or left to right? There should be two answers. Okay, you have to relate with this with the linear one. I'm getting some answer.
Left to right, sir.
Sir, would you
Sir,
please
right to
tell
left.
the question again?
Huh?
The question টা আরেকবার
Left to
বলবেন?
right.
Sir, right to left motor.
Okay, so you see here the armature will when it will move in this direction, which will be faced first? Okay, so here we have drawn A to B, B to C, C to D, isn't it? So here we have drawn A to B, B to C, C to D. But armature rotating in the opposite direction, isn't it? So armature will rotate from A to D to C, C to D as a motor. As a motor, it will rotate in anti-clockwise direction. But the distribution, when we are drawing the distribution, we have taken clockwise. But the motor, as a motor, the machine is rotating in anti-clockwise direction. Okay, so that means the answer, what is the answer? Correct answer? Bole dao.
Right to left.
So right to left. So this is the direction as a motor, and generator is left to right. Generator, as a generator, it will rotating, it is moving from left to right. So it's okay. Now you just tell me that if already I have marked the pole tips, then as a motor, which pole tips is getting more flux and which pole tips is getting less flux?
Leading pole tips
Okay, so that means
there are more flux.
the pole tips which is faced by the armature conductor first, it is called the leading pole tips, isn't it? So that means here the leading pole tips is this. So this is your leading pole tips, because armature conductor will face this pole tips first, then this one. Okay, so leading pole tips which I have made circle. So these pole tips will be faced by the armature conductor first. And at the leading pole tips, you will get an increase in flux. And the tailing pole tips, you will get the flux is reduced. But that is the opposite for generator. For generator, a leading and the trailing pole tips concepts are different, as the direction of rotation is different. Okay, now for generator, that red circle, this pole tips is basically the trailing pole tips. Okay, so that means for generator, you will get the increase in flux in trailing pole tips and reduction in flux in the leading pole tips. Is that point clear? So that also we can write down here as an observation. So that means in case of a motor, in case of a motor, the flux voltage is increased and it is decreased at trailing voltage. Okay. Opposite is true for generator. Are these 2 points clear? Okay. Now come to the third observation. বল।
স্যার এই যেটা আপনি এটা বলছেন যে অপোজিট ইজ ট্রু ফর জেনারেটর, এটার মানে কি জেনারেটর তো উল্টো দিকে রোটেট করছে, সেক্ষেত্রে লিডিং পোল টিপস আর ডিক্রিজ
হ্যাঁ, তাহলে অপোজিট এই
চেঞ্জ
স্টেটমেন্টের
হবে
অপোজিট
না
হচ্ছে
একই
না,
থাকবে?
এই স্টেটমেন্টের অপোজিট হচ্ছে তো।
ও আচ্ছা আচ্ছা।
জেনারেটরের ক্ষেত্রে লিডিং পোল টিপসে ফ্লাক্সটা ডিক্রিজ করবে আর ট্রেলিং পোল টিপসে ইনক্রিজ করবে। ভালো করে দেখো।
আচ্ছা জেনারেটর, আমি এটা বলতে চাইছি জেনারেটর তো উল্টো দিকে রোটেট করছে, সেক্ষেত্রে
সেই জন্য তো
লিডিং পোল টিপসটা
দেখো, জেনারেটরটা উল্টো দিকে ঘুরছে, ঠিক আছে, কিন্তু আমি বলেছি এটা মোটর হোক জেনারেটর হোক এই ডিস্ট্রিবিউশনটা কখনো চেঞ্জ হবে না, ঠিক আছে। তাহলে ডিস্ট্রিবিউশনটা ফিক্সড, জেনারেটর উল্টো দিকে ঘুরছে, তো জেনারেটর যেই উল্টো দিকে ঘুরলো তখন লিডিং আর ট্রেলিং পোল টিপসের ডেফিনেশনটা চেঞ্জ হয়ে গেল, ঠিক আছে। ফ্লাক্স ডিস্ট্রিবিউশন ফিক্সড, লিডিং পোল টিপসের ডেফিনেশন চেঞ্জ হয়ে গেল। তাহলে জেনারেটরের ক্ষেত্রে ট্রেলিং পোল টিপস, মানে এই যে রেড সার্কেল যেটা দেওয়া আছে এটা হচ্ছে জেনারেটরের ট্রেলিং পোল টিপস, ট্রেলিং পোল টিপসে ফ্লাক্সটা ইনক্রিজ করলো না।
হ্যাঁ হ্যাঁ হ্যাঁ
বুঝতে পেরেছো?
আচ্ছা ঠিক আছে।
হ্যাঁ, আর আর কারো কোনো ডাউট? এইটা অনেক সময় অনেকেই কনফিউজ করো, সেই জন্য আমি একটু ক্লিয়ারলি বলে দিলাম। So I may take one more class on this armature reaction, but I don't have any uh, problem with this. Already I have taken 11 class. This is the 12th class. I think I should take 30 to 35 class to complete this syllabus if I proceed in this speed. But I don't have any problem. You should understand this machine or this rotating machine very clearly, otherwise you will not get interest in electrical machines. Okay, and whatever the armature reaction you were learning in this phase, it is similar for all the machines. When you will learn synchronous machine, there also you will you'll learn a different kind of armature reactions, but the basic concepts, the foundations are same. So remember this. Now the third point is very clear, so that I've already drawn. So here you see actually the flask is now crosses at a different point, not at GNA. So previously, when the no load distribution we drew for this field flux only, the GNA and MNA coincides. Okay, now the MNAs are at different location. Why? Because of this deformed or the deformed resultant flux distribution, isn't it? So that also you can write down as a point. The flux density at interpolar axis is no longer 0. You see here the interpolar axis, isn't it? So GNA is basically the interpolar axis. Okay, so that also you can write the flux density at GNA is no longer 0. No longer 0, but has an acceptable value depending on the depending on what? Depending on what?
Armature current.
Okay, but armature flux we can write, or armature MMF. Anything you can write. So better
Okay,
to
sir.
write armature MMF because number of turns also comes. Okay. So I think that point is clear. So this point, how much height or how much flux will be there at the geometric neutral. So this is depend on the armature MMF. Armature MMF. Okay, so how much flux will be there at GNA, and later stage you will see that this flux will create the problem in commutation. I already told you that after discussing this armature reaction again, I will go back to the commutation. So what is the fourth observation? Okay, so fourth observation is similar. So that means the shifting of the magnetic neutral axis. So the third point, I have not mentioned the shifting of the magnetic neutral axis from GNA. What I have mentioned in the third point that in the GNA, you will get some finite flux, which may create the problem in commutation. But the fourth point, under the fourth point, I will mention this, the shifting of the magnetic neutral axis from the geometric neutral axis. Okay. So let me ask somebody again, because these are all Jyotirindo Sarkar. Jyotirindo Sarkar.
Yes, sir.
Can you define this MNA?
So MNA is the point where the flux is 0.
Correct. So you have pointed out correctly. That means MNA is the point when the flux passes the 0 value, or flux density having the 0 value. Okay, so that means here MNA is this. Magnetic neutral axis. Which was at the GNA at which condition?
No load condition.
No load condition. Okay, shifted Which direction? Direction of the rotation?
In the for generator.
No.
In the direction of rotation for generator.
First you tell me as a motor, it will be shifted forward or backward?
Okay, then
forward or backward?
Backward.
In the
Backward.
So let me come to this. So as a motor, it is
Backward.
going in this direction. So that means it will be shifted backward, isn't it? You see, this is the motor direction. It is shifted backward. For motor, it is backward, and for generator, it is forward direction. Is that clear?
লাস্ট স্টেপটা একবার রিপিট করবেন?
কোনটা বলো? এমএনএটা কোন দিকে শিফট করে?
লাস্ট পয়েন্টটা ওটা শুনতে পাইনি আসলে।
I am asking that in which direction the MNA is shifted. MNA is shifted against the direction of the rotation in case of motor, or backward. Is that clear? Previously the MNA was here, so that is the actual position was the MNA in the no load condition. Now it has shifted backward against the direction of the rotation in case of motor. In case of motor, shifted backwards. Okay. And one more point, and the shift, or rather amount of shift, depends on what? Bolo? Armature MMF.
Armature MMF.
MMF.
Correct. Any question? Okay. Now the observation 5. So I think these points are very straightforward. You can understand this point very clearly. Now the fifth point is not that straightforward. You have to understand. First you write down, I will explain this. So let me see any question I have. What observation can we make from the shift of MNA of an unknown machine? Nirmallo Nandi has asked this. I didn't get your question. What observation can we make from the? You just unmute and ask me the question. I didn't get you. Nirmallo Nandi.
স্যার কোন একটা আননোন মেশিন, সেটা কোন রকম কিছু জানা নেই আমার, শুধুমাত্র তার এমএনএ আর জিএনএ থেকে এমএনএ শিফটটা দেখে কি কি অবজারভেশন তৈরি করব মেশিনটা থেকে?
কোন কি জানা নেই মানে বুঝলাম না আমি ঠিক। একদম কিছু জানা নেই বলতে?
ধরুন স্যার মেশিনটা একটা বক্সের মধ্যে রাখা আছে।
হ্যাঁ, ডিসি মেশিন বক্সের মধ্যে তো হ্যাঁ
মেশিনটা একটা বক্সের মধ্যে রাখা আছে।
আচ্ছা,
হ্যাঁ, তো সেটার ক্যারেক্টারিস্টিক্স হিসেবে দেওয়া আছে কেবলমাত্র জিএনএ থেকে এমএনএ শিফটটা, তাহলে
কোন দিকে সেটা বলা আছে?
তৈরি করা যাবে
না না, কোন দিকে শিফট করছে
স্যার,
সেটা
কোন দিকে শিফট হচ্ছে সেটাতে একটা সাইন অ্যাসাইন করে তো আমরা মোটর না জেনারেটর সেটা ডিসাইড করতে পারবো। মানে যেমন ব্যাকওয়ার্ডে গেলে মাইনাস, ফরওয়ার্ডে গেলে প্লাস, এরকম।
সেটা বুঝলাম, আর কি জানতে চাইছো তাহলে বলো? হোয়াট এলস
স্যার
ইনফরমেশন
আর কিছু জানা যাবে কি সেই গ্রাফ থেকে? হ্যাঁ,
ওকে, মানে কতটা শিফট করলো সেটা থেকে আর্মেচার রিঅ্যাকশন কতটা হচ্ছে, মানে আর্মেচার কতটা কন্ট্রিবিউট করছে সেটা জানা যাবে। বুঝতে পেরেছো? কতটা শিফট হলো সেটা দেখে এটা জানা যাবে যে আর্মেচার কতটা কন্ট্রিবিউট করছে। আর এছাড়া তো কিছু না, পুরোটাই তো আর্মেচার এমএমএফ এর উপর ডিপেন্ড করছে।
ঠিক আছে।
আর্মেচার এমএমএফ যতটা কন্ট্রিবিউট করবে, এবার তুমি যদি এরপরে আমরা ডিসকাস করব যে এগুলো তো অবজারভেশন, এরপরে আসবো কি কি প্রবলেম, প্র্যাকটিক্যাল কি কি প্রবলেম, what are the practical problems are introduced in the machine due to this armature reaction. Okay, so these are the observation, মানে just from this resultant curve what are the observation we can make. Okay, so these are the observation only. Now we'll go for this practical problem. Okay, so practical difficulties due to incorporated due to this armature reaction, and after that we'll discuss how we can avoid the armature reaction, or we can at least minimize the problem caused by this armature reaction. That will come later. This observation is very important. If you don't understand the actual thing, actual this observation, then you can't understand this the problem, actual problem which is caused. Okay. Now the fifth point is, here we have considered no saturation. Okay, but if we consider the saturation, then the useful flux per pole, that will be reduced. Okay, now what we have done here, so let me write down the observation first. If we consider the saturation, then the useful flux per pole is reduced. Useful flux per pole is reduced. Okay, and if we don't consider the saturation, then the useful flux per pole is unaltered. Okay, now how we can explain this point? Okay, now let me draw the BH curve. So BH curve, the starting of this BH curve almost linear, but I cannot draw a straight line in this boat. It's difficult to draw the straight line. Okay, so anyway, I'm trying. So this is called the knee point again. After that, after the point, knee point, the saturation begins. So that point is called the knee point. So before that, it was a linear. Now come to this resultant curve. You see, suppose this value was the original value of the this what is this, of the no load field distribution, is it? So this was the original value of the no load distribution. Now in this portion, in this side, the flux has reduced, and in this side the flux has increased. Now if we take because of this triangular distribution, okay, so it has some at some part of this curve it has reduced the original flux, and at some point it has increased the original flux. Now whether these two things are same, whatever the increment we get, the same we get in the reduction, or we get more in increment, less in reduction, or the opposite, we get
Sir, more
so that is
sir, more reduction, less decline.
So that is the thing we have to discuss here. Have you understood actually this point? একটুখানি
কোয়েশ্চেনটা আবার বলবেন, বুঝা গেল না।
হ্যাঁ, বোঝানোর চেষ্টা করছি। মেইন কার্ভটা ছিল এইরকম, the main curve was this. Okay, now to this you have added this linear curve. This linear curve, suppose this is a linear curve. Now if we add this linear curve, so that means you see here how much you will lose, here the same amount you should gain. If I take like this, the amount which you will lose in this side, which will lose in this side, same amount you will gain in this side. Okay, so that means that is basically added here, and you got this resultant curve, isn't it? So this same armature mmf is added with the main field mm, and you got this resultant curve. Now when you are getting this resultant curve, whether your loss and gain, these two are same, then there will be no change in the flux per pole value. মানে তুমি যতটা লুজ করেছো ততটা তো গেইন করেছো, একটা সাইডে লুজ করলো একটা সাইডে গেইন করেছো। So that means the net flux per pole value যেটা ধরে আমরা ক্যালকুলেট করি, if we can remember, so EA equals to ZA by A P phi N. So this is the flux per pole. So this value is the flux per pole that basically comes from this curve, no load curve. Okay, now if this flux per pole is unaltered, then no question of reduction of this voltage. এটা যদি আনঅল্টার্ড থাকে তাহলে এটা মানে রিডাকশন হবে না বা চেঞ্জ হবে না, রাদার রিডাকশন কেন বলবো, চেঞ্জ হবে না। বুঝতে পেরেছো? তাহলে লস গেইনটা যদি সেম থাকতো, then the flux per pole will be unaltered and there is no question of change in induced EMF, EA. But the thing is not that. The thing is different due to this BH curve. Okay, now if this is the knee point, let me draw it a little high. Now if suppose your MMF change is same, suppose you have lost this much MMF and you have gained this much MMF, these two are same, exactly same, but the effect will not be same that you can take from this B. You see here the reduction is this much, but the gain which will get from the same same MMF will be only this much. So that means though you are taking the same MMF you are taking for this loss and gain, same MMF you are taking for this loss and gain, but if we see the change in B, in the loss is more, the gain is less. Is that clear?
স্যার এই পার্টটা একবার একটু বলুন না স্যার।
বলো
এই পার্টটা স্যার একবার একটু বলুন না, ওই যেটা সেম ইএমএফ এর গেইনের পার্টটা যেটা বললেন।
Okay, now you see here, এটা ওখানে ব্যাপারটা এখান থেকে বুঝতে হবে। এখানে তো এটা এই এমএমএফ টা লিনিয়ার আছে, এমএমএফ এটা লিনিয়ার, তাহলে বা ফ্লাক্সটাও অনেকটাই লিনিয়ার। তো আমি যদি ধরে নিই যে যতটা ফ্লাক্স লুজ করছি একটা সাইডে ততটাই ফ্লাক্স একটা সাইডে গেইন করছি, সেটা যদি হতো তাহলে ফ্লাক্স পার পোলটা চেঞ্জ হতো না, কিন্তু সেটা হচ্ছে না। সেটা কেন হচ্ছে না? ডিউ টু দ্য স্যাচুরেশন অফ দ্য BH কার্ভ। যদি আমি সেম এটি চেঞ্জ ধরে নিই, সেম ডেল্টা এটি ধরি, তো দিস টু ভ্যালু এক্স্যাক্টলি সেম, তাহলে এই পয়েন্টের এদিকে ধরো ফ্লাক্স এডিটা কমেছে, তাহলে কমলে তাহলে চেঞ্জ অফ ডেল্টা বি কতটা হলো? এতটা হলো, সেটা আমি ডেল্টা বি এর লিখেছি। কিন্তু সেম এটি যদি অপোজিট সাইডে মানে বাড়ার সাইডে আমি ধরি, তাহলে দেখো অতটা বি কিন্তু বাড়ছে না। কেন বাড়ছে না? ডিউ টু স্যাচুরেশন। এটা যদি স্যাচুরেশন না হয় এরকম হতো, এটা লিনিয়ার হতো, তাহলে কিন্তু এক্স্যাক্টলি সেম বি তুমি পেতে।
ও তাহলে স্ট্রেট লাইন।
যদি স্ট্রেট লাইন হতো,
হ্যাঁ
এটা তো
হ্যাঁ স্যার,
ম্যাগনেটিক মেটেরিয়াল, এটা তো এয়ার গ্যাপ না শুধু,
হ্যাঁ তাহলে
তাহলে
হ্যাঁ
তুমি
হ্যাঁ
সেম
হ্যাঁ
বি হতো, বি দুটো
না
সেম হতো। Okay, so if we don't
হ্যাঁ
consider the saturation, then there will be no loss in the flux per pole. But as there is a saturation, so this should be the case, and that will result in net reduction in flux per pole. So that is our observation. তাহলে ওই ভোল্টেজটাও চেঞ্জ হয়ে যাবে, যেটা আমরা ধরে প্রথমে নো লোডে ক্যালকুলেট করেছি। এইটা মাথায় রাখবে। তাহলে এই যে ইএ, সরি, যে ইএ we have calculated by this formula, ZA by A P phi N. If this flux value is reduced, so this value will be reduced. So that is the major problem on armature reaction. Armature reaction এ শুধু ফ্লাক্স কমে যায়, ফ্লাক্স ডিস্টার্ব করে তাই না, ভোল্টেজও কমে যায়। So this is very important point. You should understand this point very clearly.
Okay sir, thank you.
Okay. Okay.
Okay sir.
So these are the observations. So 5 observation I have made. You should read all this very clearly and carefully, so that don't miss any point.
স্যার
বলো।
স্যার ওই স্যাচুরেশনটা হচ্ছে এটা আমরা কি করে বুঝবো?
স্যাচুরেশন বোঝার দরকার নেই, ম্যাগনেটিক মেটেরিয়াল মানে তার
এখানে তো আমি
স্যাচুরেশন হবে। এবার যত তুমি হাই
হ্যাঁ
আর্মেচার
সেটা তো
মানে যত তোমার এই এভারেজ, তুমি তোমার এই পয়েন্টটা যত বেশি হবে, তত তোমার স্যাচুরেশনটা বেশি হবে। বুঝতে পেরেছো? আমরা যাই এদিকে, তাহলে বুঝতে পারবে। স্যাচুরেশন ডিপেন্ড করে অনেকগুলো পয়েন্টের উপর। ফার্স্ট পয়েন্ট হচ্ছে তুমি what is the মানে minimum, what is the maximum value you have taken for the main field. ওকে, এই ভ্যালুটা তুমি মানে আগে থেকে অনেক বেশি নিয়েছো। কেন বেশি নেবে? তার কারণ হচ্ছে তুমি যদি কম নাও, তাহলে তোমার মেশিনে আয়রন বেশি লাগবে, কপার বেশি লাগবে। বুঝতে পেরেছো? তুমি এটা একটু কম করে নিলে, যেটা আগে থেকে এই মানে মানে অপারেটিং পয়েন্টটা তুমি অনেক নিচে সিলেক্ট করেছো। সাপোজ দিস ইজ দ্য বিএইচ কার্ভ। হ্যাঁ, তুমি আগে থেকে এই যে জানো যে সব হতে পারে বলে একদম নিচের দিকে একটা পয়েন্ট নিয়েছো, অপারেটিং পয়েন্ট। হ্যাঁ, তুমি এদিকে যাবেই না। বুঝতে পেরেছো? তুমি অনেক নিচের দিকে পয়েন্ট নিয়েছো। ঠিক আছে, নিচের দিকে পয়েন্ট নিলে তো পুরোটা লিনিয়ারে পড়ে গেল, মানে বাড়া কমা পুরোটাই লিনিয়ারে পড়বে। বুঝতে পেরেছো তো? সেই ধরনের তুমি যদি তাহলে মেশিনটা ইনএফিশিয়েন্ট মেশিন হবে। মানে প্রচুর কপার, প্রচুর আয়রন লাগবে, তোমার ডিজাইন হয়তো খুব ভালো, কিন্তু কেউ নেবে না, কেউ কিনবে না মেশিন। বুঝতে পেরেছো? মানে কস্ট উইল বি ভেরি হাই। মানে সেম সাইজের মোটরের কস্ট অনেক বেশি বেশি হয়ে যাবে, তাহলে আয়রন বেশি, কপার বেশি লাগবে। তাই এটা তোমাকে আলটিমেটলি যেতে হবে সেই নি কার্ভের কাছাকাছি অপারেটিং পয়েন্টটাকে ফেলতে হবে। যেই ওটা ফেলবে তখন যখনই আর্মেচার রিয়াকশন হবে, তাহলে একটা সাইড কম রিডাকশনটা বেশি হবে, ইনক্রিমেন্টটা কম হবে ফ্লাক্স ডেন্সিটি। দ্যাট ইজ দ্য প্র্যাকটিক্যাল প্রবলেম। হতে খুব ভালো হতো আমরা যদি সবকিছু আইডিয়াল ধরতাম, মানে পুরো লিনিয়ারে আমার পড়ে গেছে জিনিসটা। মানে বিএইচ কার্ভে তো অনেকটা পোর্শন লিনিয়ার থাকে, পুরোটাই যদি লিনিয়ারের মধ্যে হয়ে যেত তাহলে খুব ভালো হতো। কিন্তু সেটা করলে কি হবে বলতো, সেটা করলে মেশিনের কস্টটা এতটাই হাই হবে যে মেশিন কেউ কিনবে না।
ওকে
সেই জন্য এই প্রবলেম গুলো থাকে। দিস আর দ্য বেসিক্স প্রবলেম।
মানে স্যার লাস্ট পয়েন্ট ইনডিরেক্টলি ফিল্ড ইএমএফ এর সাথে বেশি রিলেটেড, মানে বেশি এফেক্ট করে ফিল্ড ইএমএফ টা।
ফিল্ড এমএমএফ, হ্যাঁ ফিল্ড এমএমএফ তো বটেই, আর্মেচার এমএমএফ টারও কিছুটা রোল আছে। মানে এই যে কতটা বাড়লো কতটা কমলো সেইটার মানে যত বেশি তোমার আর্মেচার এমএমএফ হবে তত পার্সেন্ট অফ রিডাকশন ইন ইএ উইল বি মোর। বুঝতে পেরেছো? মানে ধরো এটিটা এতটা না হয় এটিটা এইটুকানি হলো, এইটুকানি এইটি হলো, তাহলে কি হবে? তাহলে এই অতটা লসের রেসপেক্টে মানে গেনের রেসপেক্টে লসটা অতটা বেশি হবে না, ফলে ই এর পার্সেন্ট অফ ই এর রিডাকশনটা কম হবে। বুঝতে পেরেছো? ফলে কিছুটা রোল এটিরও আছে, মানে আর্মেচার এমএমএফ এর রয়েছে, কিছুটা রোল ফিল্ড এমএমএফ এর রয়েছে। Now we'll discuss the effect, practical effects. Effects of armature reaction. The first point is that I mentioned in the last point. So, reduction in EMF. Okay. So that I already explained. So here also you can write that flux per pole is reduced and therefore reduction in EMF. Okay, so this is the point I have already explained to you, that why the reduction in EMF. The next point is increase in iron loss. The value of the iron loss. Now you know that what is iron loss. Do you know what are the iron losses?
Sir, eddy current loss and hysteresis loss.
So have you studied this in which class you have studied this?
Sir, in 12 and in previous semester.
Okay.
Sir, you have only taught us.
I have only taught you. Okay. So in
transformer and transformer.
Correct. Even the transformer discussion I should tell you, because here also you have another transformer, isn't it? In this machine one. So class, whether the class has been started for the transformers by Eddie sir?
One class.
So he has taken only one class. So I think he will now we will continue with this class. Okay, so anyway, so for iron loss, you know there are two types of losses: eddy current loss and hysteresis loss. Okay, now eddy current loss depends on what? What are the things on which eddy current loss depends, and what are the things on which the hysteresis loss depends? Anybody?
Frequency and
So
the
magnetic flux frequency. Magnetic flux frequency.
Okay. Not magnetic flux actually. Frequency, anyway, frequency will
Field
not change.
density.
Here the frequency depends on speed. So therefore it will be constant. or constant speed operation. But another most important thing on which these two losses depend, that is the maximum flux density, dm. That means the flux density level. So on the flux density, the losses depends. Okay, now here you have seen in that resultant distribution, the result that maximum flux density, as the maximum flux has increased and as the areas are constant, so the maximum flux density has to be increased, isn't it? Though I have drawn only the flux distribution. Okay, now in the resultant flux distribution, you have seen the maximum value of the flux has increased. Okay, and as the maximum value of the flux has increased, as the area is constant, so maximum flux density will increase. So as it has increased due to this armature reaction, so the eddy current loss will be increased as well as the hysteresis loss will be increased. Both the loss will be increased because the maximum flux density has increased. Clear? Okay. So these are all practical problems. You will get reduction in MMF, you will get increase in iron loss. The next point is sparking. Sparking at the commutator surface. Sparking at the commutator surface. So why the sparking will occur? For that, I should tell you that due to the armature reaction, you have seen that in that location where you generally place the brush. Okay, so there you have a finite voltage or finite from the curve you can see that there is a finite flux. If there is a finite flux, then what will be there? There will be a rotational EMF induced in the coil. Okay, now for commutation, there should not be any voltage induced in the coil which is going under the commutation. That point I already mentioned during the discussion of commutation. Now, if that is not the case, if there is some voltage in the coil going under commutation, then what will happen? And if that voltage is go beyond 30 volts, okay, so then there will be a sparking. Is that clear? So that means you have this type of segments. So these are the enlarged view of this commutator. So these are the mica. So these are the mica separators. And these are called undercut commutators. So this is the copper portion. This I am drawing the commutator. Commutator, and this is the mica separator. Mica separator. Okay, so if the voltage between the conductor connected to adjacent commutator segment is beyond 30 volt, if it is beyond 30 volt, then the sparking occurs. That means arcing. So that means arc occurs. That means this very thin mica separator cannot withstand a voltage above 30 volts. Is that clear? I think you have seen some DC machine, and also you have seen some commutator. And if you have seen the commutator, then you will see that the hello হ্যাঁ আমি এটা হ্যাঁ না আমি এটা ক্লাসে আছি হ্যাঁ আমাকে একটার পরে ফোন করো ওকে so if the voltage between the conductor connected to two consecutive commutator segments is beyond 30 volt, then there is every possibility of uh, puncturing this mica insulation, and there is every possibility of sparking. Okay, and that occurs this possibility of voltage which is more than 30 volt, that possibility comes due to the voltage at the commutation region. So that means if I go back to this thing, okay, so here actually I will place my brush over here, isn't it? But there actually, if the flux is zero, ideally the flux should be zero, because at the no load condition you have seen the flux is ideally zero there. If the flux is ideally zero there, then no question of EMF. So EMF is also zero. So that these are all ideal things. But due to the armature reaction at the point where it is supposed to be zero, the flux is supposed to be zero. Now there is a finite flux over there. So due to this finite flux, as the coil is rotating in this flux, there will be some rotational EMF in the coil. Okay, now this rotational, the coil having this rotational EMF is connected to the commutator segments. Okay, and between two commutator segments, if the voltage is going beyond 30 volt, then there is every possibility of sparking. Okay, and if the sparking continues, then that forms a ring of fire. So that means this sparking ultimately results in a ring of fire around the commutator. Sparking leads to the ring of fire around the commutator surface. So have you understood this point? Have you understood this point? Are you there in the class?
Yes.
Okay, I think today's the class is a little heavy for you, so therefore you are not responding now. So let me stop at this point, then I will continue in the next class. Okay.
Sir, I have a question here.
Bolo.
Sir,
Bolo.
sir, can we tell that? Yes, sir. Can we tell that the armature reaction causes the under commutation as the sparking occurs? All of this.
Under commutation. Okay, so under that is the
yes,
fourth
sir,
point.
in the commutation you told
okay,
about.
so that is the fourth point which I have not written here. That is the problem in commutation or the delayed commutation.
Okay, sir.
Okay, so that I have not written it, but that
Okay,
is
sir.
another point. Another point is the sparking. Okay, sparking can also be due to this delayed commutation, and sparking can be there also due to this increase in voltage. So there are two reasons for which the sparking may occur. So one cause of sparking is this, is the delayed commutation, because if we switch off any circuit before it is going to before the current going to be zero, then there is every possibility of sparking. That I think you know that. So আমাদের যে বোর্ড গুলো আছে দেখবে যে আমাদের মেশিন ল্যাবে যে বোর্ড গুলো আছে এই বোর্ড গুলোতে আমরা বলি যখনই তুমি সুইচটা অন অফ করবে তখন লোড বক্সের সব সুইচ গুলোকে অফ করে দাও, তারপরে সুইচটা অন অফ করো। হ্যাঁ, তাহলে কি হয়, জিরো কারেন্ট সুইচিং বলে এটাকে। তো জিরো কারেন্ট সুইচিং এ স্পার্কিংটা হয় না।
আচ্ছা স্যার।
হ্যাঁ, আর যদি কারেন্ট মানে চলা অবস্থায় তুমি সুইচ অন অফ করো তাহলে কিন্তু স্পার্কিংটা হবে। বুঝতে পেরেছো? তো ডিলেড কমিউটেশন কি হয়? So actually that commutation is like this, though it should be like this. তো এইখানে মানে এটার আগে হট করে তুমি এখানে বন্ধ করে দিচ্ছ in case of delayed commutation. So therefore the possibility of sparking there. So that I will discuss in the next class. So that I have not written here because I think whatever we have discussed today is, can be little bit heavier for all the students. So therefore, I am just stopping myself here. I will continue in the next class. So this point you can say the delayed commutation that I am not discussing today.
Okay, sir.
Okay. So any question you have on whatever we have discussed today? Okay. If you don't have any question, now let me record the attendance.